Evening, everybody. It's 5 o'clock Thursday night. Time for some Calc 3. Hope everybody's doing well. Excuse me. So last time we looked at double integrals, right? We talked about what they give us, which is the area under a surface above a region in the XY plane. Nothing about that's changing for today. We're going to still look at double integrals, as you saw in the lesson. We're just going to do it now in polar coordinates, because depending on our region, polar coordinates might make it easier to do. So here's my plan for today. I'm going to talk a little bit about double integrals and polar. Just a little bit about the substitutions, and we'll look at an example where we change into polar. But I think a lot of today we're going to spend in your groups, because I know some of you guys are still working on the problems from 14.2. And then I've got a couple problems for you to try from the 14.3 worksheet. So I really want to give you guys some time to just practice the double integrals in your groups, and I can come in and answer any questions to make sure that you guys are feeling comfortable with those. Because next week we'll be looking at applications of double integrals, and then we're going to start to talk about some triple integrals. So we really want to get this week down because it builds a good foundation for where we're heading. All right. So as always, as I'm going through these topics, feel free to ask questions. And when you're working in your groups, if you guys are getting stuck or having some issues or just have some questions, call me in and we can take a look at this stuff. Because like I said, the better we get this week down, I think the better next week will go as well, just because next week builds on this week so much. All right. All right. So let's dive in. All right. So on Tuesday, the region we were integrating over was given in rectangular coordinates. We saw if it was a rectangle, it was actually our favorite case because all of our limits are constants. But if one or more of our limits are defined by a function, we plot the region and we work from there. Okay. We're going to look at some situations today where it may be easier to define our region in polar coordinates. Most notably, if the region is symmetric to the origin. So the main ones we're going to look at today is when our region is circular, because polar handles circles much easier than rectangular, right? Every point on a circle is the same distance from the origin. Whereas when we're doing rectangular, our distances are measured horizontally and vertically from the origin. So we've talked a little bit about polar coordinates. And just as a reminder, if we have a point in the plane, it can be defined as xy or r comma theta, where r basically stands for radius. It's the distance from the origin, and theta is the angle made with the positive x-axis. All right. Now here are our conversions. Just like with the midterm, and I'll always remind you, don't feel like you have to memorize all these conversions. These can go on your note card for the final. We just need to know how to use them. And these are straight out of trig. X is our cosine theta, y is our sine theta, and r is the square root of x squared plus y squared, which is basically just the Pythagorean theorem. And tangent of theta is opposite over adjacent, or y over x. So really we're just using some trigonometry to help make these things a little bit easier. All right, so let's talk about the kind of regions. Don't worry about that right there, but let's talk about the kind of regions where things are going to be better in polar. Now, here's a very, what I think is a very straightforward example of when polar becomes advantageous, okay? So let's say we wanted to do a double integral over this region here, this circle, okay? So we're integrating some function, and I got to set it up. So, sorry. if I were to do, the circle of radius 5, if I were to do it in rectangular coordinates, let's say we do bottom to top first. So that means I'm going to be integrating over some function f. Maybe it's a function of x and y. And I'm going to be doing bottom to top first. So I'm going to be doing dy first. This could be done bottom to top or left to right. It's going to look very similar. So now I need what this curve is in rectangular. Well, just as a reminder, and it comes actually right from the substitution. Remember this, x squared plus y squared equals r squared is our formula for a circle centered at the origin. So we'd have x squared plus y squared equals 25. And what we would have to do is solve this for y. You're going to get really used to seeing this over the next, actually few weeks. Because when we solve for y, we get 25, we get the square root of 25 minus x squared. Now, the thing is, if that's all I have, that only accounts for the top half of the circle. So when I'm solving, I end up taking the square root of both sides. So that introduces the plus minus, the negative being the bottom half. So the lower limit would be negative square root of 25 minus x squared to positive rad 25 minus x squared. Whoops. Okay, so those would be our inside limits, bottom to top. Now we're going to go left to right, and we're going to do our x's. Well, the minimum x can be is -5. The maximum x can be is +5. Now, these aren't that concerning, but these limits could be. Now, it does depend on what our function is, because if our function is something like y, so it'd be y squared over 2, then these aren't so bad. But if our function is just 1 or a whole lot of other options, these limits can make this thing really messy. So that's why we also look at it in polar. So let's look at its equivalent in polar. So the first thing we do is we would substitute for the x and the y. So x is r cosine theta. Okay, so let me back up. So the question came up, why are the x limits just -5 to 5? So let's talk a little bit about, well, first off, one thing to think about, and this is just from a practical standpoint, we need those outside limits to be constants, because otherwise we won't get an answer. If those outside limits still have functions in them, because we don't plug these in until after we've taken all our antiderivatives, we would get left with variables in our problem. Now let's talk about why they're constants from a more conceptual standpoint. What's going to happen is, because our lower limit is this curve and our upper limit is this curve, we're basically integrating on our way up from this curve to this curve. And then while we're going from -5 to 5 in the x direction. Okay, so that's why we can have our inside limits be functions, but our outside limits end up just being constants. It's kind of hard for me to draw on here, but basically the way that I think about it is, as this is, I'm going from this lower limit to this upper limit, and my x, so the y's are going up and my x's are staying between -5 and 5. So probably not the best explanation of why our outside limits are constants, but all the variability is taken care of on our inside limits. That's why our outside limits get to just be constants. And we can, and guys, as we go on, feel free to ask that question again, maybe not right now, but let that sink in for a little bit. And you'll get really used to it. Like, the one thing I want you to take from this is even if you're not exactly sure why right now, just know that your outside limits have to be constants. Otherwise, we can't get a value. But I'm happy to talk more about that down the road if it's still kind of not making sense as we're going through these, because we'll see similar stuff again. Okay. So back to here. So we're switching it over to polar. Y is going to be our sine theta. So any function we have in there, any x's and y's, we're just going to straight up substitute in r cosine theta and r sine theta for x and y. Now, here's where this thing gets really cool. Because it's a circle, all of our limits are going to be constants, and we can do r first or theta first, because r is going to go from 0 out to 5. All right, it's going to go from the very beginning out to 5. And then theta is going to go from 0 to 2 pi, since we're doing the full circle. And as you can imagine, it's really easy to adjust for a half a circle, would be 0 to pi, or 3/4 of a circle, or a quarter circle, so on and so forth. Now we did r first and then theta. And you saw this in the video. When we're doing the dy, when we're changing over the dy dx, we have to put an r in there. And so r dr d theta. That is every time. Every time you do every time you do a double integral in polar, you have to include the r. It is part of the dA. All right. And I know the video in the online lesson goes through that a little bit, so I'm not going to take class time right now to do that. But if you do have questions about that later on, shoot me an email. I can send you an explanation of where the R comes from. The biggest thing though is, and I can't stress this enough, because even I do it sometimes. Don't forget to put the R in there if you're doing a double integral in polar. Make a note to yourself right now, something like this. Don't forget R. Maybe a few exclamation points. All right. That's something you'll want to put on your note card too. Don't forget that R, because if you don't have the R, 99 out of 100 times your problem will come out wrong, even though you did everything else correctly. All right. Now, let's just kind of do a real quick comparison of the limits. The nice thing that is that in polar, all of our limits are constants. In rectangular, we have these inside limits. And again, these may not be that bad depending on what our function is, but they also could be a nightmare depending on what our function is. We guaranteed these limits will be very easy to deal with. So whenever we have a circular region, we want to use polar. Now here, when we have a disk, okay, so our region is this half a disk. Trust me when I say you don't even want to use rectangular for this, because we have to break this thing up all sorts of ways. And this thing would get really messy, because, we talked the other day about a definite left or a definite right or a definite top and a definite bottom. So if you're going left, right, we have to break it up here, because here's the left, here's the right, then here's the left, here's the right, and then we have to break it up here. So to even have a chance in doing this one in rectangular, we'd have to break it up into 3 separate integrals, and they're not going to be pretty. I'm not going to go through it just because it'd be such a mess. So anytime we have a region that's the area between 2 circles, guaranteed we're going to want to use polar, because with polar, our limits actually come out quite nice. For this one, if you see what's happening with R, let's say we did R first, R is going to go from 4 to 6, right? From 4 all the way to 6. Theta It's going to go from negative pi over 2 to pi over 2. And then we'd have our function g of r comma theta, r dr d theta. Okay. So hopefully you're getting the idea right off the bat, right? If we have a circular region in the XY plane that we're integrating over, we want to do polar. Like I said, there's a good chance we can do rectangular. This integral up here, especially if we used Wolfram Alpha or Symbolab, we're probably going to get an answer. But if we had to do it by hand, it could get a little messy, whereas a lot of times these are going to be a lot cleaner. So that's a little bit of the motivation for why we have this other system for doing integrals. Questions so far? Like I said, that's just a little motivation. We're going to do another example here in a second. We'll do one of the ones from the worksheet. Okay. Then we talked a little bit about the converting. Basically what you do is you use those substitutions. If you have any X's or Y's in your functions, they get replaced with r cosine theta and r sine theta. The dA, which is basically representing that change in area. For rectangular, it's dx dy or dy dx. For polar, it's r dr d theta or r d theta dr. Okay. So basically we use those two substitutions. Like I said, I'm not going to go through this just because it was in the video and it has to do off of arc length. So what we need to do is we make our substitutions, and here's the 3 substitutions you're really going to need. Like I said, have those on your note card. They come right out of our trig. And then don't forget this r in your integrand. That is really the main parts to doing a double integral in polar. All right. So let's do one from the worksheet. Let me put the worksheet in chat so that you guys have a copy. All right, so here's let's bring over our worksheet here. I'm going to do number 2. I'm going to give you guys number 1, and then if you have time, number 3, because they're both really nice problems to practice. Let's talk about converting one. Okay. So this is number 2 from our worksheet. All right, so we're given this initial double integral 0 to 1, 0 to square root of 1 minus x squared. And like I was saying before, you're going to get really used to seeing this form, but let's go through it again, because one thing we're going to need to do is sketch the region in the XY plane, because that's going to help us rewrite it. But let's talk about what this looks like. Well, that's the equation y equals square root of 1 minus x squared. If I were to square both sides, I'd get y squared equals 1 minus x squared. Add the x squared over. I get x squared plus y squared equals 1. So this is the top half of a circle of radius 1. It only gives us the top half because of the square root. This actually is the full circle. All right. It's one of the limitations of rectangular because we have to deal with functions and a circle doesn't pass the vertical line test. If down here had been negative square root of 1 minus x squared, then we would have been looking at the lower half and the upper half of the circle. And maybe we'll take a quick look at that here after we do this one. So let's do this one and then we'll come back and look at a couple of variations. So what you want to do is get a rough sketch of your region. This can be done by hand. This can be done in a graphing calculator, Desmos, Wolfram, whatever you like. So y equals square root of 1 minus x squared. like I said, is the top half of a circle of radius 1. Now we only need the top half because the lower limit is 0. Now here's something that's interesting. X is only going from 0 to 1. So X is only going from 0 to 1. So here is our region. So we're only getting a quarter of a circle. And please use your imagination and pretend like that's circular. I apologize for my terrible half circle there. So that's our region. So let's talk about changing the limits first. Then we'll talk about changing the integrand. Now, because our region is circular, all of our limits are going to be constants. Why is that a valuable piece of information? Well, that means the order of our integration does not matter. I can do R first, or I can do theta first. I just out of habit, I always do R first. So in looking at R is going to go from 0 out to the edge of the circle, which is 1. This is 0 to 1, and I'm doing R first. So those are R values. And theta is going to go from 0 up to pi over 2 because we just have the quarter circle. So 0 to pi over 2. Our limits are done. And like I said, guys, we can change the order on these without even really having to worry about it because they're all constants. Okay, next thing we do, if there are any x's or y's in our functions, those get changed out with the substitution we saw before. I'll put them on here. So x equals r cosine theta and y equals r sine theta. The other one that we see sometimes, right, is the x squared plus y squared equals r squared. Our particular function doesn't have an x squared plus y squared, so we're not worried about this one here. Like I said, I'm giving you guys number 1, and you can already see the x squared plus y squared. So I'm already kind of giving you a hint. You're going to be substituting in r squared for all of those. All right, so our y becomes r sine theta. And now here's the part that you have to remember. When these change to dr d theta, we have to add in the other r. Again, that is our dA. That's that part that I wrote on the first sheet. Do not forget the r. I'm talking about that r right there, okay? It is always part of the dA when you're doing an integral in polar coordinates. All right, let's simplify. We're going to go ahead and do this one completely because I just want to show you a lot of these end up pretty easy, even though they look messy, because there's not a whole lot of really tough antiderivatives here. Antiderivative of r squared is r cubed over 3. So the very first thing we're going to do is take that antiderivative, have it r cubed over 3. That's going to go from 0 to 1. And we'll still have to do d theta. Now plugging in the 1, I get, oh, sorry, I lost my sine theta there. Something looked off there. That's sine theta. I don't like that notation, sorry. I want to fix this up a little. R cubed over 3. You can put the sine theta really wherever you want. The thing is, the 0 to 1, here's what you want to remember. Those are R values. They're not theta values. We'll still have something left in terms of theta, but that's okay because this is telling me I still need to integrate in terms of theta. So 0 to pi over 2. These are going to be going in for the r, so I'm going to have 1 cubed over 3 sine theta minus 0 cubed over 3 sine theta d theta. That 0 is going to zero that whole part out. This 1 cubed is just 1. So I'm actually going to, we could pull the 1/3 out of our integral. And now we're just taking the antiderivative of sine. So we have 1/3. The antiderivative of sine is negative cosine. And this is going from 0 to pi over 2. So we have 1/3. The negative cosine of pi over 2 is 0. And then negative, so cosine of 0 is 1, but we have to make that negative. So we end up with minus a -1, which turns it positive. So we end up with 1/3 times 1, or 1/3. So a lot of these integrals end up actually not being that bad. All right. So questions about example number, about problem number 2. Okay. Then, like I said, I'm going to break you into groups, and maybe start with the problem from 14.3. I'm going to put you in the same groups from Tuesday, so that way you're working on the same problems. But start with 14.3 because we just did that, and then go back and do 14.2 after you finish. One thing I'll tell you, and it's pretty cool about all 3 of these problems. After you do your substitutions and get it into polar, all 3 of these antiderivatives will use U substitution. So that's the hint I want to give you when you go to take these antiderivatives. All right. Any questions? So here's going to be, oh no, you're not doing all 3. Yeah. So here's what you guys are going to be working on in your groups. Like I said, I'm going to put you in the same groups as last time. So it's going to take me a second because it just takes a second to organize everybody. But that way you're working on the same 14.2 problems as before. And guys, again, work on these problems. If you have questions, let me know. The answer keys are on the second page on both of these. Because of what I want for today, here's what I want. We're going to do this for you're going to have the next hour to work in your groups. So yeah, there's 4 problems. If you don't get through all 4, that's okay, but get through what you can. But I want you to leave here feeling pretty comfortable with double integrals so that over the weekend, you can work on the 14.1 through 14.3 homework and build a nice foundation for next week. So make sure as questions come up that you do ask. All right, so let's get you guys into your groups. And give me just a second on this. Okay. Sorry, guys. It just takes me a second to do that. Okay, so here, I'm going to send out the room invitations now. And I'll send those problem numbers out again. I'll also send my whiteboards out so you guys have access to all that.